Remember, if all else fails, your vessel's old-fashioned magnetic compass, along with a mechanical or Dutchman's log, lead line and charts, will enable you to navigate safely without any electronic gizmos. Magnetic compasses are subject to two significant errors: magnetic variation and compass deviation. Magnetic variation is the result of the Earth's magnetic field not being precisely aligned with its geographic axis, running through the poles, which means that depending on where you are, your compass needle might point east or west of true north. If it points west of true north, it is suffering westerly variation. If it points east of true north, it is suffering easterly variation. For example, in the Solent, magnetic variation is presently around 2 degrees west, whereas off the west coast of Ireland it's 8 degrees west. And if you were sailing a great circle route from the British Isles towards the east coast of the USA, you would suffer 20 degrees or more of westerly variation on your passage. On the other hand, if you were enjoying a Baltic cruise, you'd find that your compass needle would be pointing east of true north. Because the Earth's magnetic field is caused by its molten iron core, which is in flux, it moves around and the amount of magnetic variation changes slowly, but continuously. When your instructor was first navigating in the English Channel in the 1970s, magnetic variation was 7 degrees west, and because electronic navigation hadn't yet filtered down to yachts, you had to get it right or you'd end up seriously off course. One way to discover the value for local variation is to examine the compass roses on your chart. For example, the rose in the north of Dawson Bay, roughly in the centre of the southern peninsula on your RYA Chart 3, tells you that in 2005 magnetic variation at its centre was 7 degrees and 25 minutes west, changing by 8 minutes east each year. So, for example, in 2010 it would be 6 degrees and 46 minutes west. Remember to use base 60 arithmetic. Of course, in practice we cannot measure within a degree, and much less so steer a course to this level of precision. So in 2010 we'd round this to the nearest degree, 7 degrees. Please note that even though 2010 is long gone, and if you performed a similar calculation today, you would arrive at a rounded figure of 6 degrees, all the exercises that go to make up this course are predicated on using a variation of 7 degrees west. Take a look at this chart in the area north of Diamond Reef. You'll see an area delineated by a purple squiggly line, with plus or minus 15 degrees written in its middle. This is an area of local magnetic anomaly, where a magnetic compass might suffer a random error of 15 degrees either way. Such anomalies are usually the result of large deposits of iron ore in the Earth's crust. There's one in the vicinity of Rockall, 190 miles west of the Outer Hebrides, if you ever happen to be just sailing by. Compass deviation results from the vessel's own magnetic field deflecting the magnetic compass from aligning precisely with magnetic north. If we imagine a wooden vessel with copper nails and no ferrous metal on board, then if the vessel steers directly towards magnetic north, her compass needle will also point at magnetic north, assuming of course that the compass is correctly aligned within the vessel. However, if she has her own magnetic field, resulting from ferrous metals being used in her construction, for example her keel, or her machinery, such as her engine, then it might be considered that there is some point in her overall structure which is the sum of all these things, and it is her centre of magnetism. Her compass needle will be deflected towards it. You can see that in this case the yacht's centre of magnetism is on her starboard side, forward of her main steering compass, and with her on a course equal to magnetic north, her compass is deviated 3 degrees east. If on the other hand she was steering a course of 180 degrees magnetic, her compass needle will be deviated 3 degrees west. The amount of deviation will therefore vary with her heading. A vessel's deviation is recorded on her deviation card and is normally plotted as a graph. Take a look at the example of a deviation curve given inside the back cover of your RYA Training Almanac. Of course, you'll never find a curve in a real almanac because each vessel has its own unique curve. Electrical circuits, radios, instruments, chart plotters can also cause deviation. And the problem with this type of cause is that it can come and go as equipment is powered up and down. So these types of equipment must be located well away from the compass. All this is pretty futile, however, if you inadvertently bring objects such as tools, sailing knives, and especially anything containing magnets close to the compass. Check to ensure that the person on the helm has not got a mobile phone in their pocket. At day skipper level, whilst you need to be aware of the existence of compass deviation, you are not expected to allow for it in your chart work. However, you must take account of compass variation whenever you measure a bearing with a hand-bearing compass and want to plot a corresponding position line on the chart, or when you calculate a course to steer and need to give an instruction to the person who's steering. Imagine we're in the RYA training world where magnetic variation is 7 degrees west of true north and that you've used a hand-bearing compass to measure the bearing from your vessel to this isolated danger mark and get a reading of 236 degrees. If we simply dialed 236 degrees into our chart plotter and plotted a position line, it would be 7 degrees out. To get it right, we have to subtract the variation, 7 degrees, before we plot our position line. 236 minus 7 is 229 degrees. Let's look at this in a little more detail. Imagine we have measured a bearing of 135 degrees. Again, this is relative to magnetic north, so we would say 135 magnetic. Or, if we were writing it down, we would add a capital M suffix. This is 135 degrees for magnetic north. So, if, for example, magnetic variation were 2 degrees west, then the true bearing would be 135 minus 2 equals 133 true. So the rule is, when variation is west and we're going from compass to true, we subtract variation. Notice that we've added a T suffix, and from now on you should get into the habit of suffixing bearings or courses with either M or T according to whether they are magnetic or true. If, on the other hand, we were sailing in Sydney, Australia, where magnetic variation is 12 degrees east, then we'd need to add the variation for the compass bearing to arrive at a true bearing. The rule is, when variation is east and we're going from compass to true, we add variation. Until now, we've concentrated on converting from magnetic to true, the flip side of which is true to magnetic, such as when we plot a course on our chart and need to instruct the person steering to steer a course according to the magnetic compass in front of them. If the course we need is 045 true and variation is 7 degrees west, then we need to add variation in order to come up with a magnetic course. The rule is, when variation is west and we're going from true to compass, we add variation. Finally, if variation is east and we're going from true to compass, we subtract variation. It's all highly confusing, isn't it? You might keep a copy of this matrix to hand, but it would be better if you could construct it from scratch, wouldn't it? Fortunately, there's a well-worn mnemonic to help you remember the rules. Cadet. Cadet stands for Compass Add east, true. If you can remember this, then you can create the tool. Try it out with these values. Click the button to reveal the answers. Some yachts, particularly those cruising in high latitudes where magnetic compasses are pretty ineffective, are starting to install GPS compasses, which are not subject Some yachts, particularly those cruising in high latitudes where magnetic compasses are pretty ineffective, are starting to install GPS compasses, which are not subject to variation or deviation. However, they are of course reliant on the GPS system and a power supply. The ultimate solution is the Gyro Compass, invented by Sperry in the 1940s. However, their price rules them out for all but the largest yachts. This one cost over €9,000. Your hand-bearing compass is also subject to variation and deviation. However, it's impossible to create a deviation card for it because it might be used in any one of many positions on board. So it's important that the crew member taking bearings positions themselves well away from objects containing ferrous metals, radios, loudspeakers, etc., and that they don't have a mobile phone in their pocket close to the hand-bearing compass. Imagine we're approaching this island and wish to find out how far off we are. We can take 3 bearings. There's a south cardinal on 283 degrees magnetic, an isolated danger mark on 273 degrees magnetic, and a west cardinal on 259 degrees magnetic. By plotting all 3, remembering to convert the bearings from magnetic to true, we can get a pretty good fix. With more than 2 position lines, it's rare to get a common intersection, and the resulting triangle is often called a cocked hat. It's good practice to assume that you're in the corner of the cocked hat nearest to danger. When selecting objects to take bearings on, try to use things that are close rather than a long way away. Just 1 degree of error at 6 miles would place you a cable, which is 1/10 of a nautical mile, from your true position, whereas a 1 degree error at 0.6 miles is only 1/100th of a nautical mile, about 20 meters. Take bearings on objects ahead or astern first, and objects abeam last, because the bearing of an object abeam will change faster. Try to get the best possible spread. When 2 charted features line up, we say that they are in transit, and this provides a very accurate position line without using the hand-bearing compass. And you can combine sources of information in order to plot a fix. In this case, with the isolated danger mark and lighthouse in transit, a calculated height of tide of 2.8 meters and a depth of water of 28.8 meters, we can plot a pretty good fix. A GPS can give position in 2 ways, either by latitude and longitude, or, if you are navigating by waypoint, the bearing and distance to the waypoint. We'll cover waypoint navigation in more detail in the lesson on electronic navigation, but basically a waypoint is a position which you've programmed into your GPS. It might, for example, be positioned just outside the entrance to your destination harbour, or on a theoretical point which keeps you clear outside dangers off a headland that you are intending to navigate past. Note the abbreviations BTW for bearing to waypoint and DTW for distance to waypoint. Actually, it's good practice to plot a fix both ways, as it's all too easy to make a mistake plotting by latitude and longitude, especially if you're tired, in poor light, and when the fix is a long way from the latitude and longitude scales on the sides of the chart. Of course, waypoints don't have to be positioned on charted features, but they must be plotted carefully on the chart and checked again, and ideally checked by another person if they're critical to safe navigation. Your instructor was once sailing single-handed from Falmouth to the Solent. By the time he was approaching the Needles Channel, just after low water, it was blowing force 6 from the southwest and thick fog with visibility less than 100 meters. He was very tired. He'd programmed a waypoint just south of southwest Shingles Buoy into the GPS and was using it to plot regular fixes. When, by his reckoning, he was about a mile from the waypoint and making nearly 8 knots over the ground, he noticed that the depth was rapidly decreasing, and he thought he could see breaking waves ahead. Very fortunately, a deep instinct told him there was something badly wrong, and he immediately put the helm down and clawed south. With too much sail up, the boat was heeled right over on a beam reach as he sailed through large breaking waves on the Needles Bridge, passing just east of the bridge westerly Cardinal Buoy. Had he continued on course, the outcome would have been very messy, probably involving lifeboats and helicopters. Analyzing the situation afterwards, he realized that he'd programmed the waypoint 1 minute, in other words 1 mile, north of his intended position. That's just 1 digit out. Had he plotted position by latitude and longitude as well, he'd have spotted his error miles away. Not only does this illustrate the danger of inputting an incorrect number and not cross-checking fixes by latitude, longitude, and bearing and distance to waypoint, but also that over-reliance on GPS can be extremely dangerous. So always try to validate a GPS fix by some entirely different means. In poor visibility, radar is the perfect solution, but if you don't have it, ask yourself whether the depth stacks up with your GPS position. In the pre-GPS era, a prudent skipper would have assumed that his or her fixes were inaccurate and would have either approached the Needles Channel very slowly on a safer course or headed somewhere else entirely. One useful shortcut is to program the center of a compass rose as a waypoint in your GPS, and then use a piece of paper to construct a ruler using the latitude scale. Note that you put 0 in the middle of the ruler. You can then place 0 on your paper ruler next to the waypoint in the center of the compass rose and swivel it round until it lines up with the bearing to waypoint on the opposite side of the rose to your position, and measure off the distance. This is much quicker and less error-prone than plotting by latitude and longitude, or even using a chart plotter and dividers. However, it can only be used on relatively large-scale Mercator charts because, as you learned in the lesson on charts, the scale varies with latitude. Every fix must have the time and log reading written alongside it. If you are navigating to a waypoint, it's not a bad idea to enter the bearing and distance to the waypoint in the deck log every time you plot a fix. But don't get tempted to fall into the trap of failing to plot the fix on the chart, as it's only by doing this that you can see whether you are sailing into danger. Well done. You've completed the lesson. Now go on to complete exercise 3